Hello, so there is not so many people. I see that we have 3 persons now. Are you listening? Could you hear me correctly?
Yeah, I hear you.
Okay.
My name is Ferrier.
Hi, Theodoros. Okay, so if you can hear me correctly, I think that I will start, even if we have only 3 persons. Again, that it can be useful to do it, and other people may have the link to have the access of the replay of it. I will maybe make it a little bit shorter that I have scheduled first. Can all of the 3 persons connected can clearly hear me? You have a space where is mentioned discussion. This allows you to make some public discussion during the presentation or private discussion just using the other parts with option. You can only contact 1 person. So there is 2 persons connected, Said and Theodoros, with a microphone. So you can speak during the presentation. Everybody will hear you. And the person connected with the letter M, I don't know who is this person. He don't have the microphone. I don't know if he can hear us. But you can ask your question in the private area or the public one. So I will start the presentation, even if there is only 3 persons. I think that it can be useful to do it instead of postpone to another day. So for your information, this year there will be 7 webinars. Hoping to get more people next time. The next one will be given by Enzo Martinelli from University of Salerno in next 14th of January. At the same time, Enzo will be in Lyon and will present the webinar from our university. The following one will be given in February about shear strengthening by Joachim Barros. He has already done one last year. And there will be new webinar coming from Australia with a field application of FRP in bridges. There will be also development of standard design equation for more full FRP system. Brahim will do again the presentation about durability in April. And then we have the webinar of Thanasis from University of Patras in April about seismic retrofitting, and quite maybe the same presentation will be given by Luc Bisbee about fire behavior and specific fire of structures strengthened by FRP. About our university, we are located in Lyon. It's in the southeast of France. It's a university, quite big university in France with 35,000 students. Essentially, the university is well known in the field of health, less in the field of technical. There is some international opportunities in our university. There is a lot of possibility for funding, essentially for European people, for example. And so keep this in mind if you are maybe interested by visiting us. About our lab, we are a small team. I'm in charge of this lab. The team is made of 11 persons, essentially associate professors, and we are working only in the field of FRP material for construction. Today, I would like to speak about FRP material at first, about mechanical properties. I will try to go quite quickly on this part, and to focus more on bond issue and try to make a small literature review and give you some new results we have on this topic. So to start with FRP, I think that we have a small community today. You are all aware about FRP system used for shear strengthening, flexural strengthening, confinement. These materials are well known in the field of construction from nowadays, essentially to protect old structure or to upgrade structure that need new strengthening because of overloading. It can be used also to solve some problem about some design mistake, for example. And for example, for seismic application, there is also a good application for to make structure more safe. In France, for example, we have some interesting development about the dynamic loading about bridge piers that are impacts with big heavy truck, and a lot of piers have been strengthened by FRP to avoid the collapse of the bridge quite successfully. So generally when we use FRP, it's an unidirectional fibers bond onto a support using a polymer, but you, I think, are aware about this. So this technique is well used in a lot of countries, and in France there is about 7 to 8 companies that apply about 50,000 square meters of carbon fibers each year, essentially in building and few applications also on large dams and bridges. We have some photos about this kind of applications, some large machine to apply the polymer and so on. So this is only example in France. So about FRP materials, I will try to go quick on this part because of the low, there is not so much people connected. You all know that FRP material are light, high strength, they are corrosion resistance, and they can be used nearby on all surfaces, and that make this material very useful in the field of concrete structures. These materials are well known in other industries, such as automotive and aerospace, and the development of this material get higher and higher each year since about 15 to 20 years, and now it's quite common in the field of construction. FRP material is made of fibers, mainly carbon, because people start with these fibers, but also with glass and few examples with aramid fibers. Matrix is essentially epoxy, and then the material you get is such kind of material with a lot of small fibers that play the same role that steel rebars, but with lighter properties. So about the fibers, you may be well known that carbon fibers, high modulus or high strength is commonly used. Generally, if we compare this to steel properties, main problem we have is that we have a higher tensile strength, but a lower Young modulus. And for this reason, The first fibers that have been commonly used is low modulus carbon fibers. Nowadays, for some specific applications, e-glass, even if the young modulus is lower than steel, seems to be quite good to dissipate more energy, and we'll see this in some large applications about seismic retrofitting, for example. If we look to these three kind of fibers, there is carbon, aramid, and glass. Carbon have a very, very good properties for all the mechanical and physical properties we may have a look at. Glass is also good, but the problem is the low Young modulus of this material and the long term with creep sensitivity and also fatigue, which is less effective than carbon. So about the polymer we use, polymer is a specific material well known in the chemistry industry, but generally in our field it's less known. A lot of misunderstanding is done because polymer needs to be very careful and specific, worried about. And there is a polymerization process that should be clearly understood. It's like concrete. We need some days, we need some specific temperature, and we need some specific humidity to get the perfect chemical reaction and get the good material at the end. Main typical properties that people need to understand is the temperature sensitivity of this material. If we compare this to concrete, we know that the concrete is full strength and full hard if we mix cement and water, and then the mechanical properties not really depends about the temperature. In this specific case, the temperature change the mechanical properties of the polymer. You have a range of temperature where the polymer is thermoset with a glacis plateau where the mechanical properties, essentially young modulus, is constant. Then there is a decrease, and to get the rubbery plateau where the properties exist but are very low and much lower than the initial one. And this may be compared to the material used, for example, to build a road. It's material coming from the petroleum industry, and it behaves in different ways depending on the temperature. So we identify a value which is the glass transition temperature of the polymer corresponding to the value where the mechanical properties decrease. So a common thermoset polymer used in our industry is epoxies, used for wet layup applications of laminates and dry fibers. It's very good materials for adhesion and bonding. We'll see this in the second part. Vinyl ester is also used, but more to build FRP rebars and to use for thermoset application. It's more expensive, and building FRP by pultrusions. So FRP is a mix of fibers and matrix, and the mechanical or properties of FRP will depend on the matrix, as I mentioned, on the fibers, but also on the amount of fibers we'll have in your mix and the adhesions. So if we look to the mechanical properties, you have to understand that the mechanical properties of UD fibers are given, and you can have very good properties of fibers. And then you will have two things to understand, is that the fibers are bound together. So there will be the problem of physical and chemistry properties of the surface and the interface between the fibers and the polymer. And then you have the laminate. So it means that you will have a lot of layers, and all those layers have to bond together perfectly. Then if we go to the mechanical properties of the resin, you can observe that generally the laminates and the mechanical properties of the FRPs essentially depends on the mechanical properties of fibers itself. It means that polymers are then just there to make sure that all the fibers are bound together and that all the fibers work in the same time in tension. So those materials are applied by wet layup method. Dry fibers are bound onto the support, and an epoxy polymer is used to impregnate the fibers. And it can be also bound using polymers. About properties, as I mentioned first, the Young modulus can be easily calculated here using quite mixture properties. It means that your final properties will depend on the matrix properties and the fibers properties. If we compare the Young modulus of the matrix and the fibers, you can observe that even if we have 70% of the FRP that is made of matrix, the mechanical properties will essentially depend on this ratio, which is the carbon, for example, Young modulus, which is nearby 200,000 megapascal. If we compare it to the one of a usual epoxy is only 3,000 megapascal. So the difference is nearby 100. So that the mechanical properties of your FRP will be depending on this value and of course this one. If your ratio is very low, your final properties will be very low. Will be very low also. So then when we have this, generally we identify the mechanical properties of this using perfect bonding between the fibers and the matrix. This is not often the case, so there is some problem in certain case between matrix and polymers, and this is well known and well identified, and then it's quite common now to get a very specific treatment of the fibers so that there is a very perfect bonding between these two, so that it allows you to make mechanical properties considering usual elastic properties of all the constituents. Then about shear, when a fiber will be fully impregnated by fibers, then there will be a bond issue between fibers, and then there is a strength. There is a strength properties to identify, which is the strength, the shear strength that can be developed around fibers to make sure that two layers will be fully bonded. Another thing that is well known in this field is that when we use these unidirectional FRP material and that it is tested in another direction, we rapidly lose the mechanical strength for a very, very low angle. It means that the decrease in Young modulus or strength is very high, and this material should be only used in the direct and in its own actual properties and not in another actual, which can be a problem mainly for a full FRP system. But in case of strengthening, generally the fibers are bound in the action where the force is applied. So to sum up the mechanical properties, you have here the stress-strain relation in tension of fibers. Matrix, I mentioned that there is a big difference. And then if you clearly observe, you can see that the FRP material will have a final property that will depend on the amount of fibers and matrix you put, and also initial properties of these both. And for nonlinear behavior, they can exist some development have been done in this field recently. This can be obtained depending on the matrix properties, but also on mixing fibers with different behavior. For testing material in our field in construction, it's quite very well identified now. Generally, everybody used this ISO norm for tensile test. There is also a STM standard, which is a little bit different in its sizing, but it's quite very similar in the principle. Coupons are made of unidirectional material, and then it is tested directly in tension. Some people ask about the durability issue of those material, and for example, this is a results coming from our lab testing. We get the questioning about the FRP durability questioning from French nuclear agency, EDF, that were quite wondering about using this material for strengthening some big buildings and chimney in nuclear power stations. And they asked us to make some tests with quite difficult weather conditions. At first there is full water during 30 minutes, then freezing, about -20 for an hour, then heating, 60 Celsius degree, then UV, then rain again, cold, heating with moisture, dry heating, and going this for 300 times. This is, I think, the only norm I found about accelerated testing of material. It is commonly used to test painting material, sorry. And we have used this for several FRP material. And what we found is that if we compare the ultimate strength and the ultimate Young modulus, we didn't find any modifications on such coupons we tested in the lab. We made about 100 tests, and we didn't notice any difference between and after the aging, and the aging was quite difficult. Brian Brenmockham will introduce some durability issue about this, and we are quite confident on the durability issue about the FRP itself. But as I mentioned, this material is bonded onto a support, and generally it can be bonded with two material, laminate material, prefabricated, and or different sheets directly bond onto the support. And so now the issue is not only to test the material, but to evaluate if, depending on the way that the material will be applied on the support, depending on the way that the man worker will be applying this material and the weather conditions and so on, we are worrying about how to identify the mechanical properties of the FRP onto the concrete. So this is the next step of my presentations about bond issue. So bond is important for a beam because when you will strengthen a beam with a FRP for flexure, for example, all of these can work if perfect bond adhesion between FRP system and reinforced concrete is assumed. It means that you will have a continuity of strain between the steel, for example, and the FRP. Other issue which is important is that in the end of the FRP system, there is no debonding because perfect bonding can be assumed in the current part, but if there is debonding of the laminate, the system won't work anymore. So bond issue onto the concrete substrate is very important. So about this, there have been a lot of development. We are aware that if we look to this, for example, this comes from the aeronautic industry and mechanical research, we know that at the end of the lap joint, we have some important stress, essentially because we have two different materials bound together with different mechanical properties. About this, you have such kind of image showing you that the shear is the main issue and the main problem. And this shear, generally in the field of reinforced concrete beams, is known to get the full delamination or peeling off of the structures. And so, in order to identify this, there have been a lot of development and modeling to try to know how to behave this interface, try to identify the mechanical properties. And this is the next step of my presentation. I will try to show you how does a researcher try to find and identify the mechanical properties of this interface. So since 1992, first research developed such kind of compressive shear test. This test has completely disappeared. We don't find it anymore. We have some single lap shear test. It's quite commonly used. It's quite difficult to, in certain cases, to apply because you can have some flexural behavior, and the mechanical properties is quite difficult to obtain. Then Towson, for example, have developed such kind of single lap shear test. The sample is connected to a block, and then here a force, a compressive force is applied and a tensile one here, so that shear will be developing in the interface. Another common test is the double lap shear test. Two concrete blocks are connected by FRP material. Then the tensile stress is applied onto the concrete, and then due to the tensile force developed in FRP, you will have shear here developing in the interface. The first authors that used this test was Okeno in 1995. It's quite a long time from now, and this kind of tests have been fully used by other authors. For example, if you look to the results obtained with such kind of test, you have here average shear stress developed all along the bonding length, and here strain in FRP. And as you observe, there is a quite linear behavior. Then debonding starts, and the full failure is then obtained. So if we go back to literature review, the first tests in papers that were reported was the paper from Towson in 1997. This was the single lap shear test I mentioned, and the test was developed for FRP bonding, but also for steel bonding. At that time, steel plates were still used for reinforced concrete strengthening. If we bond onto the surface here some strain gauges and follow how does the force will be transferred from FRP to concrete, this author has shown that and this is quite commonly known now, that depending on the level of load you applied, you will have a transfer length which is quite very low. You can observe here that nearby 100, 150, 200 millimeters is enough to transfer the full stress from the FRP to the concrete. This graph shown that at the beginning of the lap joint you have important strain. This strain decreases when the stress is transferred to the concrete support to be nil at the end. You can observe the author catch the debonding here with the full stress was developed here all this zone is debond, and then we get the failure. But in the elastic stage, the bonding length is not so long. We only need 100 to 200 millimeters to bond this material onto the supports. This is mainly due to shear transfer. This is also some old studies done mainly in the field of aeronautic with authors like Volkersen or Art Smith. When we use very basic equation, shear is due to difference of displacement with two materials, steel and concrete, for example, and the angle of rotation is commonly known the shear strain. And basically, you can write those equations and equilibrium between two sections, and this allows you to calculate the shear stress depending on the length. And if you do this calculation and compare this to the strain, it's very well developed in the field, in the paper from Talstein. You can observe that you have very important shear stress decrease for very few here centimeters of bonding. And this is also a problem because very locally you have very peak stress, important stress that can make some specific mechanical disorder for the failure. So this work done by Al Smith have been developed again by Talstein for the concrete FRP problem. Bizindawi works on it, and a lot of specific equations have been developed on this topic. You can find them in the literature review quite easily. More recently, other authors works on a very local bond slip mechanical laws. All those authors have shown that if you look at the peak stress only, this area, I mean, if you focus your study on this area, you are able basically, based on the experimental study, to show that the bond stress against the slip can assume this kind of law, a nonlinear law with a decrease which correspond to the beginning of the debonding. And they have identified this kind of mechanical law. Depending on the authors, you will find several proposals. And I have sum up in this paper coming from, this is the problem coming, the paper, sorry, is the one mentioned here. And this paper sum up all the equation proposed by different authors. And they have clearly observed that the maximal value can be basically depending on the concrete strength. And based on this, they have proposed some mechanical relation to calculate the ultimate load that you need to design such kind of bonding properties. So depending now on the design, there is several mechanical law. Generally, this value is correctly assumed, and also the G factor is also proposed in several papers, so that you have some bond slip model that can be used after that. A comparison has been done by Stinge, Matisse, and Agnello. This study is quite very interesting because you compare a lot of tests. If you have to develop some bonding issue, I recommend you to read this paper because you have a lot of results coming from the literature and a comparison from the ultimate calculated value and experimental one, clearly showing that all the the calibrate model are quite good, depending on the test and depending on the fitting you get. But we can observe that there is quite very good results, or whatever is the mechanical relation used for this. Then what have been done using these properties, Shalal and Chen, also Kenneth Neal in University of Sherbrooke, have then tried to use this kind of local bond slip model into structural analysis. You have FRP, interface behavior need some specific relation for interface model, and for this the calibrate relation have proposed in the literature have been used to investigate if this bonding issue can be modeled at the level of the structure to catch essentially the problem of failure, which is the important issue for the strengthening of beam. And also these both papers are very interesting. So now we have seen that under static load, this problem of bond is quite well identified under static load. There have been a lot of other studies about creeping behavior and fatigue issue. When you strengthen a building, such as a parking slab, for example, on this slab there will be creeping load, and you will have also fatigue load due to cars. And the main problem coming from the engineering field is the evolution of the material properties, and does the evolution of the bonding, for example, will affect the structural behavior. So, for example, I have done this work during my PhD some years ago. You have these concrete blocks test in shear for 1 million of cycles. The full fatigue was done between 60% of the failure and 10% of the failure for 1 million of cycles. This test is the double lap shear test that I've described before I've used. You can observe here the results we get. We can observe that depending on the level of strength, you have quite slight, no real evolution of the mechanical properties till we have 100,000 of cycles, and then there is a slight increase of the slip. Here is the slip increasing, but at the end, even if the slip increase, we didn't get the failure of the concrete. When the test is done after 1 million of cycles, you have the static loading here. This picture is quite old. What we observe is that we have some decreasing in properties in the adhesive because the failure modes change between a cohesive to a non-cohesive failure. And for this, it was very interesting for us to see the mechanical decrease and the fatigue. Since then, there have been, of course, other studies done. I can mention, for example, this one in 2008. This is fatigue behavior of block connected by anchorage system. And this one clearly observed is also a very interesting paper done because they have tested several systems, only bonded system, a small anchor system, mesh, fibrous anchors, and also bond, try to bond straps onto the surface. And those authors has tested all this configuration, has also observed an increasing in the slip, as I mentioned first, and they also seen that there is a slight decrease. Other tests done this time by Christian Carlonia. This is an interesting paper because it observed the fatigue process with a non-destructive, with a full field image analysis, allowing to get the strain along the bond length. And you can observe here that the bond length again is very short, only about less than 100 millimeters, and they have observed this all during the fatigue issue. So this study is also very interesting to see if you are interested about the fatigue behavior of the adhesive. At the end, what we have when fatigue issue is concerned, what we are interested in is to get the ultimate stress strength, the strength on the material, depending on the numbers of cycles. And for the designers, for engineers, this value is interesting, is to know what is the limit of the stress you should have on the FRP to avoid any fatigue debonding. And in this case, in literature, you have some equations such as this one, like Euler curves, that propose some constant, of course, depending on the process and the system you are studying. But there is some proposal. There is not so much, but there is some proposal allowing to know about the fatigue behavior. Then the second issue, which is interesting to focus on, is the creep issue. This was one of my part of my work done during my thesis also. And at that time, we were interested about getting the full master curve of an adhesive using the time temperature principle, basically based on the William Lender and Ferrier hypothesis that it's possible to get the full creeping relation using short-term tests with different temperature. The idea here is you have during a short period a temperature giving you a creeping curve. If you increase the temperature, you will accelerate the creeping problem, and then the creep will increase. And when you increase again the temperature, you can get several curves. Those authors is on the 1950s, have shown that it's possible then, if you translate all of those single curve, to have the full master curve of a polymer for reference temperature. So we have used this idea on lap joints made of epoxy polymer and carbon fibers. You have here all the shear properties of the adhesive that we obtain from 20 Celsius temperature, then 25, 30, 35, and so on, until we get a real decrease of the mechanical properties. And then we translate all of them to get the full evolution of the shear during in function of time, Basically, when you have this, you have the creep function for several temperature. And we compare this with long-term tests, and this has been also published and it works quite well. At the end, what is interesting is that if you basically use some specific rheological model, you can fit your parameter in comparison with the experimental data we get. And using this, you are able to get the shear strain evolution depending on the initial shear stress and the creep function you have. And what we imagine with this is to say that the creep strain, the shear strain, depends on the instantaneous strain and the creeping one. It means that if you identify the initial shear strain you have in the adhesive, if you apply the constant stress, and if you know about how does this strain will change during time, you are able to fix the minimal value of shear stress you should have in the adhesive to keep elastic your lap joint. This was the idea to fix an allowable shear strength to limit to get this kind of figures here, depending on time, depending on level of strain, depending on temperature, you will have the limit in stress you should have in your FRP, not in your FRP, but in the adhesive, to avoid to get the nonlinear behavior, to keep your adhesive in an elastic stage. And if we observe here this value, for example, at 20 Celsius degree, our conclusions were that we should limit at 0.7 megapascal the serviceability limits stress in the adhesive, so that we avoid any debonding in a long time period. But if we speak about higher temperature, you can observe that the limits should be much lower. So since then, and more recently, there have been also other studies done about creep. There is this one that I founded and think that is also a very interesting work done on small specimen. This is maybe the only problem about this paper. The specimens are very small and the size effect can be questionable. You can have here the testing device allowing to apply the shear. And which is interesting is that the modeling has been done as I have done, and that they have proposed also to try to improve the behavior, the creeping behavior, using nano carbon particles that can be used in several kind of polymer used in the field of aeronautic to improve the creeping behavior. And these authors conclude that they can be very interesting to use some new polymer to limit the problem of creep in this adhesive. So this paper that it can be very interesting also, and quite a very new paper. So the problem that we found is that the problem of temperature dependency is quite important if we use at the problem of creep. And more recently, 2 years ago, we have started to combine the problem of thermal properties dependency and the problem of loading. It means that the adhesive is sensitive to temperature. Shear modulus decrease and there is a change in shear strength. Due to change in temperature, that can induce also displacements between concrete FRP and adhesive, because all those materials don't have the same thermal expansion factor. And this may induce internal stresses and some additional shear stress that have not been studied. So what we have done is trying to identify about the local bond slip model I have mentioned before. How does temperature can affect this? I mean, all the proposed equation I mentioned before, are they only good at 20 Celsius temperature, or are they good for any current temperature? So this study is very recent. I have presented it at the CICE conference in Vancouver last summer. What we have done is combining stress and in a heating chamber temperature. We have tested about 50 samples with different temperature conditions, and we have tested 2 different FRP systems. To identify the way that strain decrease along the bonding length, we have bound several strain gauges, allowing to get the full strength in the FRP and then to get the load transfer. Then with this study, a wet layup system have been used, carbon fibers, and laminates wire bond onto the surface. two different properties. This one has a quite high glass temperature properties that were very interesting in this study. Then, example of results obtained, for example, by laminate. You have here load and full displacement obtained, for example, with the wet layup method. In this case, you can observe that when we are from 0, -10, -40, 20 Celsius degree, 40, between -40 to +40, there is nearby no change in mechanical properties. There is a slight increase of the stiffness for very low temperature and a slight decrease in strength, but it's not so, there is not so many change. But when you reach 60 Celsius degree, remember that the glass transition temperature is about 75 for this polymer. The decrease starts, and then at 80 Celsius degree, you have a very important decrease with non-linear behavior, mainly depending on the FRP. Same observation with laminates. The temperature was higher. You can observe here that we start to get some important decrease for only 100 and 110 Celsius degree. But interesting results is for lower temperature. It seems that there is a decrease in strength for -40 Celsius degree. It can be maybe explained due to more important internal shear stress in the adhesive due to the important difference of temperature between concrete, laminate, and so on. If we look to the strain distribution, you can observe here at the same level of load, the different strain profile we get for the wet layup application. We can observe that we have quite classic strain distribution range for a range of temperature from -40 to 40. But when the temperature increases, you can observe that the length that you need to transfer the forces is increased, and that the transfer of forces is very different with a lower strain at the beginning. So the load transfer length is changed and depends on the temperature, which is quite new because all the equations basically have been developed for a constant value of transfer length. For the other system, same observation can be done, different value. You can see that very low temperature increase very locally the strain. That may explain that we get maybe some initial internal strain that allow to maybe create some debonding before the loading. And then that the behavior becomes very smooth when we increase the temperature. Nearby glass, we are below the glass transition temperature, but we are very nearby this value. So temperature modify the local bond slip model. That is our main conclusion and main issue about this, because the local bond slip model essentially depends on the strain profile you have. About failure mode, here you have the one get by -30. You can see that the system, all the concrete block are freeze. The test was done with the temperature and the loading at the same time. So it was in a thermal chamber. And then when the temperature increased, we get a very non-cohesive failure with full debonding on the FRP system. Same observation with laminate, cohesive failure, and then non-cohesive failure at 120 Celsius degree. So main parameter that should be modified to consider the temperature effect is the GF value and the value of beta depending on the bonding length, and also the factor alpha here. So these works done are quite very new for us, and now we are working to try to build new model to introduce the temperature effect in the bonding. In fact, if we don't do this, you can see here, for example, one model which works quite well, coming from Yao and the team of Tang. These authors publish a model that works very perfectly. And when you observe this, you can see that for low temperature, the value at failure are underestimated, which can be quite dangerous. For common temperature ranging from 0 to 40 Celsius degree, it's quite good. But since we increase the temperature, for very low temperature, 60 is not so high. The previous calculation value is very far from the results. And the same is for laminate. Laminate is good for 20 Celsius degree. And the model is calibrated for this value, but for low temperature is not good, and for high temperature is not good also. So this is an important problem because we can have low temperature and load for bridges and other kind of applications. So we get back to modeling and try to see what was what did exist in literature. We found a lot of model about bond issue in literature, quite old model. All these models try to introduce temperature in the shear behavior to model the mechanical properties. And if we look, for example, Art Smith, it's a researcher coming from aerospace and works a lot of bonding problem. He introduced a problem introducing that there can be terms in the shear stress distribution due only to thermal problem, and also plastic strain due to local debonding. He has calibrated all these constant value depending on the variation in temperature, difference in value of the thermal expansion factor and conductivity of the material. And basically, depending on those calibrated value, if we use his model and try to identify basically based on our results the ultimate load, we can observe that this model doesn't work. It means that when the temperature increases, the ultimate load should be much higher than the one we observe in his model. And if we compare to the obtained results, it's very different. In fact, the problem is that Art Smith works on thermoset polymer, and that the temperature was much far from the glass transition temperature. It means that all his model have been calibrated on the glacis plateau. It means that it cannot be used in our condition because in this term, you have here young modulus of the epoxy polymer, note here, and this value is not constant because it will depend on the temperature. So we have done several tests only on epoxy coupons to identify the mechanical properties of epoxy in function of temperature. And basically, if we correct by introducing a temperature dependency of the factor in the model, the calculated value are more clear. The value obtained are very next to the experimental value, and we can even observe the fact that when low temperature is introduced, a decrease in the ultimate load is noted, mainly because there is internal stress in the FRP due to the non-dilatation of the FRP. The thermal expansion factor of FRP is nearby 0, while concrete and epoxy increase in strain due to the change in temperature or the reducing in temperature. And the internal stress in the adhesive creates prematurated failure. This load is the mechanical load we apply to get the failure of the specimen. Do not consider the internal stress we have due only to change in temperature. So at the end, I think that we are nearby the end of the presentation. We have a better view about the how to bond those very nice material onto concrete. And this material is a very nice way to strengthen structure. I think you are quite all confident about it. But otherwise, even if the mechanical properties is well known, there is also other factors. And to finish, I will want just to mention other paper I found quite interesting for to outline. You have this paper. I didn't mention, sorry, the authors of this paper, but I can send it by email if some wanted. This author have studied the effect of the surface treatment. All the surface treatment recommended are water jets, centrifugal. There is also a mechanical surface treatment, and this author compare different surface treatments to identify the effect of the surface treatment. And as you observe, it seems that sanding is not the most efficient way to prepare the surface. With the same system, if you use water jet, you can observe that the ultimate stress you have is much higher than the one obtained by only sanding the surface. It means that the bonding is more complex than we thought, that the concrete preparation should be looked at very carefully, and maybe such kind of also surface preparation should be introduced in the model, because from now, nobody really care about how the surface is prepared. We need to prepare it, but don't know really if this affects the ultimate bonding load. There is another paper that is also very interesting, introducing the concrete quality and the porosity of it. I mean, if you have a lot of aggregate and different size of aggregates and cement paste, this is different surface that have been prepared. You may have different failure modes and also different failure value. This paper is very recent and very original, and propose something that is new. I didn't know about it. Is a size, aggregate size depending about the ultimate load. This author has shown that the more larger is the aggregates, the lower is the ultimate load at failure you will get. Essentially, because about this small graph you have here, showing that depending on the porosity of the surface and the amount of cement paste, the strength of the complex is completely changed. So to go to the conclusions, we have shown that FRP materials are efficient materials, well known. A bond issue is a very critical and may be studied a little bit furthermore, mainly about concrete substrate maybe. And fatigue, creep, thermal behavior is already studied. Some additional research could be done in this field, but we are quite confident in the field of fatigue and creep issue. Durability, fire issue is always questioning we have from the engineering field. People always are aware about the durability, about the fire, but the more the material is used in the field, the more that we are confident in this field. So next step is to see how we can strengthen bridges to hope that we don't have such kind of event. And so the next webinar in this field will be given by Enzo Martinelli next week at the same time. I think that I will advise again about it and maybe more to be able to get more people. So you have all the opportunity to make some open discussion. We can take a few minutes if you have. Otherwise, I would like to thank you to be here. We are always all listening to each other. If you are speaking, everybody is able to hear you. If you have any specific question, I would like just to put the next series so that you have them. If you have any question, open discussion you want to make about it, everybody is able to hear you. If not, well, hope to see you next time. Are you all still here? Okay, so I can see that okay, so if you don't have any question, I would like to thanks to follow this presentation. This presentation will be able to have in I can send you the presentation if you are if you just want the presentation. I can send you the one I have prepared. You just have to send me an email. I will put here my email so that you can send it to me. If you are aware about to make it in replay for your students or your colleague, if you are a student, I will send you and put in the IIFC website the link to have the access of the replay of this webinar. Okay, so thanks to you, and you just have to shut down your visit to the webinar so that the record stage will start. It will start when all the students will leave the room, so you have just to leave the webinar, to disconnect it, and then it's okay. Thanks all to you, and see you.
You are currently the only person in this conference.